All right. Hello, everyone. It's 9 o'clock, and welcome to the Inorganic Ventures webinar series for 2021. My name is Brian Alexander. I'm the Chief Technical Officer at IV, and on behalf of the entire company, we want to thank you for being here today. Today, we're going to be speaking about washout considerations for ICP analyses. We have two of our most experienced technical staff presenting today. The first will be James King. James is our Director of Production. He's an inorganic chemist with experience in synthesis and purification. His research is focused on the characterization of organometallic compounds that are used as molecular magnets. James is a native of Hampton, Virginia, and received his undergraduate degree from North Carolina A&T State University and a master's degree from Virginia Tech. The second presenter is Thomas Kozikowski. Thomas is one of our most experienced research and development chemists. He has expertise in all things related to the manufacturing of inorganic metal standards, stability and homogeneity, technical support, and all of those details. His other experience covers reagent synthesis and purification, trace metals analyses using ICP techniques, transpiration studies, and container cleanliness. Thomas has two bachelor's degrees, one in chemistry and one in forensic science, and both are from Virginia Commonwealth University. The presentation will take about 40 to 45 minutes, and afterwards we would love to hear from you if you have any questions. If you do have questions at any time during the presentation, we would ask that you please submit them using the Q&A function in Zoom. And then once the presentation is over, we'll read those questions out and give Thomas and James the opportunity to answer them. So again, if you do have any questions, please just write them down in the question and answer feature in Zoom, and we'll take care of those at the end of the presentation. So with that, we'll go ahead and get started, and James will kick us off. James.
All right, thank you, Brian, and good morning, everyone. Like Brian said, we're thankful that everybody is here today. We're gonna go through some washout considerations for your ICP analyses. You can go ahead and go to the next slide. So some of the key topics we're gonna go through today, I'm gonna kick us off. We're gonna go through a number of the different causes for washout and memory concerns. This is gonna touch on a number of different topics, including intro systems and introduction systems for your ICP instruments, matrix considerations, and different elemental compatibility concerns. And it'll be, we're gonna try to see how we can tie those together and kind of give you a sense of how these things can affect your analysis from a washout and memory standpoint. At that point, once we get through the elements of concern, we'll kick it off to Thomas and transition to him, and he'll start talking about some strategies to mitigate or eliminate memory effects associated with washout problems, and he'll also be providing maintenance recommendations. All right. So we truly want this to be more of an interactive discussion rather than just a straightforward PowerPoint presentation. With that, we'll be polling the audience throughout just to get a sense of what kind of instrumentation, what kind of challenges you all are experiencing in your labs as we go throughout. So go ahead and go to the next one. So we're going to kick it off with a question. What type of instrument do you use in your laboratory? An optical ICP and mass spec, or are you using both? And we'll give you just a few seconds to kind of answer that. Apparently hosts and panelists cannot vote. All right, so we've got, it's pretty kind of standard across the board. It's about a third of you are using both. That's interesting, okay. And it's split, the other ones are between mass spec and OES, so that's good to know. All right, so go ahead and go to the next one, or the next slide. All right, so these are some of the main causes for washout problems in the ICP instrumentation, and we're going to go through each of them and try to tie them together. So it ranges from solution matrices, whether these are driven by what's commercially available or your specific methodologies for your preparation, sample preparation and whatnot. Elemental affinity, elemental compatibility has a huge effect on washout, particularly in the ICP instruments. We're going to tie that to pump tubing, intro systems, things like that. And then rinse protocols as far as what acids and bases to use, and also things like timing for your settings in your instrumentation software. We're going to touch on all of these things as we go through the presentation. So next. So when we talk about solution matrix, when we talk about ICP standards, sample preparation, from what we found at Inorganic Ventures, that most elements, they're stable using nitric. Most customers require or ask for their standards in nitric acid. And we believe that's mainly due to the fact that there's minimal interferences, particularly on the mass spec associated with nitric. However, there's some elements that customers and that we deal with that require maybe HF for stability. There are problems with different elements that we'll go into. There are some elements that require HCl for stability. And there are a few that have issues with HCl or issues with HCl in solution, but we'll go through those and we'll kind of show you what kind of solutions we can provide for those. There are also some analytes that require basic media for ICP analyses. So we're going to dig into each one of these. We can go on to the next one. Okay, before we go into the different matrices, we have a second question for you. Does your company forbid the use of hydrofluoric acid in the laboratory? And we'll give you just a few seconds to answer that. Okay. Well, let's see some of those results. Okay, so that's good. That's a encouraging thing. We've run into a number of clients in the past that for regulatory reasons or otherwise, they were forbidden from using hydrofluoric acid in their labs. So you can go ahead and go to the next slide. And for those that are somewhat still limited in what they can do, just as a side note, we'd encourage you to speak with your regulatory representatives, because it's not having HF as available as an option, particularly when it comes to digestion and things like that. It just seems somewhat of an unnecessary impediment from our standpoint. So when we talk about hydrofluoric acid and the different elements that we could put in solution as far as ICP, I've always been fascinated with what we can do with HF since I've worked here. So we generally kind of divide all the elements up. You can see the white ones, we don't mention those because they're largely, HF doesn't matter to those guys. You can put them in to HF containing solutions. They're perfectly fine and stable. The ones marked HF elements require some degree or some amount of hydrofluoric acid to stabilize them in solution. We've also got the ones marked in pink that say to avoid HF. These are your calciums or your group 2s and your rare earths, where the presence of HF in the right concentration can destabilize those guys. But then we've got in an interesting group, what we call the HF thieves, elements like boron, aluminum, and arsenic, and they can really cut both ways. Where you and we could go on talking about elemental compatibility, but from a high level, things like aluminum and boron, they can actually strip HF away from some of these hydrofluoric acid bearing elements like a titanium or zirconium. It could actually wind up destabilizing them in solution. But on the flip side, on the other hand, you could actually use those to your advantage, where you have a situation where you have something like silicon, germanium, tin in a solution, but you also need to put something like calcium and maybe a rare earth. You can actually leverage those HF thieves to your advantage to soak up, so to speak, or steal some of the free HF that's in solution, and you actually can wind up stabilizing a number of different things that otherwise you wouldn't be able to stabilize. To bring this back to washout, all this matters because how you stabilizing your elements in solution should be one of your top priorities, to make sure that you don't have washout issues from elements falling out of solution as they're literally in the tubes or going through your instrumentation sample introduction systems. You can go ahead and move on to HCl. Okay. So fun fact about hydrochloric acid, there are actually more elements on the table that are comfortable or happy in hydrochloric acid than there are even in nitric acid. And that's mainly due to the precious metals uh, that are more comfortable ultimately, and mercury to an extent, but they're more comfortable ultimately in HCl than they are in nitric. And you've got a couple that they're not all that stable in HCl, but things like silver, thallium, lead, but they can ultimately be that instability can be mitigated. Um, Silver, all you need to do is increase the concentration of HCl relative to the amount of silver you have in solution. For thallium, if your certified reference material producer has access to thallium 3 plus starting material, they can use that, and thallium will be just fine in HCl. Um, but this circles back to just the same thing we mentioned about HF, where you have to make sure that ultimately whatever you have in solution is going to be stable, because otherwise you're going to have washout issues if you've got solid literally sitting in your tubes going through your introduction system and into your instrument ultimately. Okay, next. We mentioned analytes that require basic media for analysis. The main ones are bromide and iodide, mainly done on the mass spec. We do have some other analytes that can be in basic media, such as molybdenum, tungsten, but they have to be kept basic. So we actually have and provide solutions of these two that are in basic media, but once you add them to acidic media, you'll have to fluorinate in order to keep them stable in solution. All right. So now we're going to touch a bit on introduction system components. So the first one we're going to talk about is spray chambers. There are the what we call the classical borosilicate spray chambers. And the issues you'll see here are mainly with boron and silicon. If you have any HF in any solution that you're using and it's going through a borosilicate glass, you're going to have issues with washout with those two elements because they're going to be leaching out of your spray chamber as a solution is passing through. On the other end, if you're using an HF resistant system like PTFE or made from PFA, if you have high levels of things like boron and silicon, and particularly mercury in a nitric matrix, matrices, those can stick around and stick to the plastic, and what you'll see is they'll effectively release over time as you run different matrices through, and that can kind of add to your washout issues. The coating is essential. We have a really good partner that we work with for our HF resistant systems, and we'd be glad to field kind of any questions afterwards about any kind of issues you might be seeing with HF resistant systems. I'll just mention double pass spray chambers. Those happen to increase your washout time due to their the physical configuration associated with those. You can go on to the next one. So question time again, what kind of spray chamber do you use for your primary ICP instrument? And we'll give you just a moment to answer that. Okay. Okay, let's see what we got. Okay, not surprisingly, most of the majority are using borosilicate glass cyclonic type of spray chamber. So we do have some HF resistant systems represented here. So, okay, so let's go ahead and move on to the next one. Okay, so sticking with the introduction system, when we talk about sample delivery, there are generally two routes that are used to get the sample into the spray chamber and ultimately into the nebulizer. Peristaltic pump, where the sample is introduced from an auto-sampler probe through a peristaltic pump tubing before it reaches the spray chamber. And what we've seen is we have a number of different elements that can stick to the PVC peristaltic pump tubing. Alternatively, there are also syringe or direct drives that have switching valves associated with them. It gets rid of the issue with the PVC peristaltic pump tubing, although you do introduce another avenue, which is the switching valve. And you need to make sure that you keep that clean and make sure that's maintenance properly, so you don't have issues with any elements sticking to the whatever material that the switching valve is made of. So You could basically kind of make an argument for either, but both have their positives and negatives. So one more question. What kind of sample delivery system do you use on your primary ICP? And we'll give you just a second to answer, or a few seconds to answer. Okay, let's see what we got. Standard peristaltic pump. Okay, so that's the vast majority kind of have the kind of that standard peristaltic pump kind of system. So good, and that's and we use that. We use both systems in our laboratory, so we have a good amount of experience with both. So let's go ahead and move on to the next. So we're gonna kind of go through just a little bit of data here. I wouldn't get too hung up on the numbers, but this is basically the testing method for our trace metals analysis, where we run 3 blanks. We run our sample, a spike, and then we run blanks towards the end. So these numbers have been, you can see that we've got 2 runs for each mass, one with a peristaltic pump, one with the syringe drive. The numbers have been normalized through the spike values. So you can see just from the numbers from a high level that we have a lot more washout issues associated with the peristaltic pump method than we do with the syringe drive. And Thomas did a really good job of kind of representing this graphically. If you can go to the next slide. So you can see that bismuth is by far one of our worst offenders here, but you can see graphically that when we use the syringe drive, we're having a lot less issues with stickiness of elements and washout and memory effects. Now, for someone like me that goes into the lab about once every 5 months to run a random sample here or there, when I run a sample and I want to wash it out and I forget about it and walk away for 10 minutes and go do something else, that's fine. But for most labs, they're looking for more for high throughput. So definitely the syringe drive would be ideal or more ideal for someone who needs that high throughput when you're running 50, 100 samples in different runs or per day. So and the syringe drive is also helps with less maintenance over time when you're running those samples with higher total dissolved solids. So all right, and I'm going to kind of end my section just talking about a few elements of concern. So at Inorganic Ventures, these are generally the elements that we've seen the most problems with washout issues. Your borons, your silicons, selenium, tin. So if you go ahead and go to the next slide, we're going to kind of break it down just a little bit. So we've got it kind of color coded here. We have issues with things like hafnium and tantalum and tungsten. It goes back to the elemental compatibility and talking about the if you have a lack of HF, it could make those guys sticky because they're coming out of solution, meaning if you either didn't put enough HF into the working solutions going through the instruments, or you have elements like boron or aluminum stealing that HF away, we could have issues. Silver was one of the classic ones. If there's any HCl present, especially in trace amounts, you'll have silver precipitating. And then if the silver chloride kind of gets into the tubing, you're going to have a hard time getting it to pass, and it's going to come out from time to time. There are a number of different elements that are marked here in orange. Nitric makes them sticky, particularly mercury and osmium. Mercury and osmium, I mean, it got to the point where Thomas and I actually made separate talks geared specifically around these 2 elements. But you really want to kind of be mindful of what you put osmium and mercury in, especially with the matrix and the containers involved. And then we have a couple that we're still kind of trying to tackle in the lab, such like selenium and thorium. And we think it might be the PVC tubing, but we don't really have much more to point to other than that. So I'm going to go on to the next one. So all this to say, as far as the problematic elements, don't run elements that you don't need that could be causing either compatibility issues for you or washout issues that could be affecting the analysis of some other elements. This is what Thomas affectionately calls the shameless plug, where we kind of talk about inorganic ventures and our ability to make custom solutions rather than your kind of standard off-the-shelf multi-element solutions that can cater to exactly what you need, where we can make higher concentration ranges that can be diluted down on the bench, or we can have ready to, shoot and dilute solutions and calibration standards that can save you time at the bench. We always push for stability uh, to make sure that everything is suitable for the methods that you're running. So, and one thing that customers are taking more and more advantage of, we can even make recommendations for elemental and matrix compatibility, particularly when you're mixing solutions down to make sure that everything is suitable for your analyses and what you're trying to do. All right, so with that, I'm going to go ahead and kick it over to Thomas. I was joking with him earlier. I said that this kind of reminds me of the typical IV day where I bring all the problems and he provides the solutions. So with that, I'm going to go ahead and kick it over to Thomas. Thank you.
Thanks, James. Yeah, he's right about that. At R&D, we deal with a lot of problems here at Inorganic Ventures, so it's never a dull day. So the next thing I'm going to talk about is common rinse solutions and strategies. So the first off, we're going to talk about your basic rinses. So most of us in the lab use nitric acid as our primary rinse, and many folks will also use HCl or a combination of those two. So if you're using an ICP OES, usually you're running higher level solutions, so 5 to 10% by volume is usually appropriate. And then folks that are using mass spec typically like to reduce the load on their plasma to make sure the lenses don't get as dirty. So we kind of keep it to 1 to 2%. Another rinse worth mentioning, we got this from Glass Expansion with their HF resistant systems. RBS 25 is a solution from Fluka. You can actually aspirate that on your OES at about 2.5%, and that will help re-wet your spray chamber. So if you look at, we saw most of you actually had the borosilicate glass spray chambers in use. You can look at it while your solutions run, and if you see, water droplets forming on the inside, that's a clear sign of poor washout issues. So the surface of your spray chamber is not working as effectively as it's supposed to. So if you aspirate the RBS 25, it's a kind of a detergent based solution, and it's also basic. So it rinses away maybe oily type substances or some of the other elements, and you'll see those droplets disappear. And then if you do a final rinse with water, your spray chamber will start working the way it was supposed to from the beginning of your run. We don't recommend using that on the mass spec though. It has a pretty high level of sodium. So if you're on an OES, you'll know that your RBS is completely washed away when all of the sodium disappears from your analysis. And then finally, we do use water, of course. It can be effective enough for some of the major elements like sodium, potassium, and calcium. We typically are using water for the auto sampler probe in the rinse station. So it's still a rinse that we use. It just not maybe for the entire rinsing protocol. So with HF, I saw a good portion of you are allowed to use HF, which is good. You just have to be careful with the intro system you're using. So you'll still want to use nitric acid as your base, so 5 to 10 on the OES and 1 to 2 on the mass spec, but you'll add HF to that rinse solution. So on your OES, you can go from maybe 0.1% to 2%, depending on which system you're using. And on your mass spec, you'll want to keep that lower, so maybe 0.05% to 0.5%. If you're using borosilicate glass for your nebulizer and spray chamber, you're going to want to limit the HF to 0.2%. No matter what level of HF you put in there, boron and silicon results will be unreliable. So you'll get bad RSDs, random good counts on one sample, and the next sample will look bad for those two elements. It's really a crapshoot. It will be good and bad, and it just won't be reliable. But it will help out with the washout of those HF elements. If you're using an HF resistant nebulizer and spray chamber, you can go a little bit higher with the HF. So if you've got southern elements like tungsten is by far the worst, as we saw in one of the previous slides, you can increase the HF to maybe 2 to 3%, but don't go any higher than that. More than 3% will degrade the coating on those HF resistant spray chambers. And that coating is essential for the good wetting, so that your analysis it'll wash out a whole lot faster. So there are a few specialty rinse solutions I think is worth mentioning. The first one, of course, is ammonium hydroxide. Most of us will rinse our ICPs with an acid solution, but if you switch it up to a basic solution, you'll get some benefits. So if you're on an OES or a mass spec, it doesn't really matter. 1 to 5% should be a good place to start. But you can use this for boron, bromide, iodide, and believe it or not, mercury. It works a whole lot better for mercury than I ever expected. HCl and thiourea, if you go 1 to 10% with the HCl and 0.5% of the thiourea, that works really well for mercury, gold, and osmium. And I'm sure not many of you use osmium. I didn't even bother putting a poll question in for that. Very small market, but we have actually developed our own standard for osmium that's going to be traceable to the SI. We're going to be coming out with that soon. But during those studies, we learned that HCl with hydroxylamine hydrochloride is the way to go. It's a great way to stabilize the osmium, but also for helping with washout when we're running it on our ICP. So one of the strategies I like to use to monitor washout is the real-time display. So most of our software packages allow you to monitor a line or several lines at the same time and actually record the signal on a time graph. And this will help tremendously with your method development activities in determining appropriate rinse times between your samples. You could maybe start out with your ICP for the first time and have a 5-second rinse and wonder, why is nothing working right on the following samples? Well, five seconds obviously isn't enough time, but this tool will help you figure out what time is appropriate. Can also help with assessing the effectiveness of different rinse solutions. So if you start aspirating a different solution, once it gets to the plasma, you'll see what's going on. So this is an example from our Spectro Arcos using the fast transient method. That's what they call it, versus the real-time display. So this, when you hit the play button, it'll start recording. And I've normalized this graph so that 2 different rinse solutions are being done. And I've lined up the data so you can see they wash out pretty effectively. So 100 ppm boron and low nitric acid over time. We want to do nitric acid rinses. So the black line there is the 5% nitric. But then I told you, basic solution works for certain elements. So boron is one of those. And when you look at the overall graph here, there's no obvious difference, but is, worth noting that there's, let's see, there we go. There's a spot here and a spot here where it increases, briefly. Those are those little water droplets that might hang from the nebulizer and they burst at some point. So that happens, and you can usually prevent that if you're using the right type of rinse. But if we zoom in, we see that there actually is a big difference between these 2 rinses. The nitric acid, which is the black line, doesn't go to baseline even within 2 minutes. So you can see I drew a line here. There's actually still a slope, and that's 2 minutes. Whereas when we use the ammonium hydroxide, it seems to be flat starting around here. So we marked 80 seconds for that. It seems to work a whole lot faster. So we can say, if we switch to this type of rinse for this run, we'll be able to get more samples run shorter amount of time and not have to worry about the washout. So in summary of those previous slides, the boron took longer with the typical 5% nitric rinse. And, James showed those graphs of which ones, to avoid with nitric, and nitric makes them sticky. Boron's one of them. Bismuth is one of them. Tungsten, osmium, elements like that. They just take longer if you don't use something else with it. So when we switched it to the base, it got a lot better. But you got to be wary of that. If you switch back to spectra mode, even that flat line still actually has a peak. So it's not actually all gone. It's just very low. So you can use the time graph to quickly determine an estimated washout. But if you're trying to verify the absence of an element, you'll need to switch to spectra mode. Next, you'll want to experiment with different rinse strategies. So what I mean by that is, switching it, using one type of rinse for a couple samples, using a different rinse for a couple more. This is actually really important when you have a switching valve or a syringe drive, because you have a dedicated carrier solution that you never change. You can't really swap another valve for that. That gets pretty complicated. But most of us want to keep that as nitric acid for whatever reasons. But for the mass spec, of course, argon chloride interferes on arsenic and selenium. So for those of you who don't use mass spec, the mass speckers, like to avoid chloride. We've got newer instruments that can handle these interferences, but if we've got the older instruments, keeping HCl away is very helpful, because of the direct interferences on arsenic and selenium. And with arsenic, if you can't use mass 75, you really can't look at arsenic. So one of the things we do to help with these strategies, run in varying order to help determine which rinses are more effective for certain elements and intro system setups. So this is an example. I know most of you probably don't use osmium, but it is one of the stickiest elements we have ever run across. So this is an example using our mass spec that actually has a syringe drive with a sample loop, a switching valve, and you can see in this picture, it is a double pass twister spray chamber. This example uses 50 ppb, not very high, but it gives you plenty of signal on the mass spec. And we're employing two different rinse strategies. So there's a red line here where we start with samples of nitric, and then thiourea, HCl, and then back to nitric, because we always want to finish out with nitric. It's the cleanest, acid and doesn't produce any interferences on any of the elements we're looking at, whereas chloride does. So the second rinse was HCl and HCl. We know osmium doesn't really like nitric, so we had the HCl rinses on the front end, and then the thiourea, and then nitric completely last. Something to note here on our mass spec, our carrier solution that pushes everything through is 1% nitric. That'll make osmium stick. It also converts it to a form that makes it stickier. So it's, instead of elemental osmium, it turns into an oxide, not necessarily tetroxide, the kind that'll, cause a lot of health issues such as blindness, but enough to actually create like a false high signal because the nebulization efficiency goes up. So the other thing is the rinse station, when it goes between samples, it goes to the rinse station. That's also 1% nitric on this instrument. So we're going to zoom in on the ones that are lower to see what's going on. So this up here is the second rinse. So if we start looking at the third, where we go to thiourea, thiourea seems to make everything go really low with counts, and that's good. So we have a second thiourea. Remember that nitric acid is running between each of these samples. And then we switch back to nitric here. We switch back to HCl here. But then when we run nitric for this last one after it already ran HCl, we get a huge spike. And that's because the HCl was kind of suppressing it, but some of that oxide formed with the initial two rinses up here. So there's some oxide stuck in the system. It might be stuck in the valve. It might be in the sample loop. And then when we ran nitric again, it changed the nebulization efficiency and gave us a really high signal. Might not actually be a lot of osmium, but to us it looks like it is. So we can't really say that it's not there. So that's one of the challenges we have. You get fooled that there's a lot of osmium there because it's changed form. So the rinse really does matter. And one thing to point on this graph is, we did calculate a detection limit at the beginning of this run of 0.003 ppb. These rinses acted with the thiourea actually rinsed it beyond the original calculated detection limit. So we had osmium in the system to begin with. It didn't look like it was much, but these rinses went even further to a better point. So definitely a good way to go for cleaning out the osmium. So I've got another question for you. Question number 5. This is the last one. Making sure you all are still awake. What solution do you use in your auto sampler rinse station? So deionized water, dilute nitric, dilute HCl, or do you use a mixture of nitric and HCl or something else? I will say though, at Inorganic Ventures, we've got several ICPs. A couple of them use nitric. None of them use HCl, but one of them actually has a dual port system, so we actually can choose water or nitric. So we'll give you a couple more seconds. All right. Most are using dilute nitric. So that's, like I said, pretty standard. A lot of the mass speccers are going to gravitate towards that. The ones that are using a mixture of the two, that's a wise move. We're going to see why in a couple more slides. And I'm curious to know what the something else might be. 4% of you said something else, so maybe we can cover that in the question and answer session. So the water, though, is good because one of the purposes of the rinse station is to actually rinse the probe and maybe not necessarily rinse your system. So some of the instruments will let you go into the auto sampler rinse station for a couple seconds, but then maybe go to a rinse bottle that has the acid that you care about for rinsing the spray chamber and the nebulizer. Let's see. There we go. So our last topic for today is going to be maintenance recommendations for your ICPs and how this affects your washout problems. So first and foremost, probably the most important is your peristaltic pump tubing. So if you're using peristaltic pump tubing for your sample delivery, consider changing it daily. Your elements will all pass through that tubing and some of them will get stuck. Now, if you're going to run something at high levels or something where you want to run something next really clean, you might want to actually change out the pump tubing right after you've run that dirty sample. And I have a really good example of why that might help you. But the peristaltic pump tubing can wear over time as well. If you do a run overnight and have it automatically shut down and the tubing is still clamped, you'll get flat spots in the tubing, and then you won't be able to push sample at the rate that you expect, and your RSDs will become poor. This is my example of changing the tubing mid-run. So this one is actually all the elements in EPA 200.8. So that's more than just mercury, but obviously I'm picking on mercury because it's one of the worst. This system is with the peristaltic pump tubing. So I had a couple examples on our other mass spec that had syringe drive, but this one just runs through peristaltic pump tubing, and it's actually quite slow. So the pump rate is, I don't even know how many RPMs, but it is very low. So with all these, we run a sample each time, and then it goes between the samples. It's going to the rinse station for only about 5 seconds, and then it 5 seconds doesn't even give that enough time to make it to even the pump, let alone the plasma. So then we do 40 seconds with 1% nitric and 40 seconds of 1% HCl. And the reason I added the HCl isn't specifically for the mercury, because this method says you're supposed to use gold, low level of gold, to rinse out mercury if you run it. The HCl I'm really using for bismuth. We've noticed that bismuth doesn't really wash out and isn't super stable unless you have nitric with HCl. So that's one of those things that use the combination of both will help with that. And that's important because everyone likes to use bismuth as an internal standard. So every single sample you run on your ICP has bismuth in it, and you might not actually be washing it out. So your correction factors might get biased over time as more and more bismuth sticks to various parts of your system. But going back to this specific example here, we're looking at mercury in this case. So this is mass 202, has no interferences with other elements that are being run here. So we run 4 samples of 100 ppb mercury, and then we run this 2% nitric, 1% HCl rinse, I think 12 times. And then that's without changing anything. So we're just doing, sample after sample after sample, and we're going to see how much it goes down. It looks fine, but it's not actually the baseline. And then we run the same solution again 4 times. So it should have relatively the same amount of sticking to the, peristaltic pump tubing, but we're going to let it rinse out, give it a chance with 2 rinses, and then at this second rinse, we're going to actually switch out the pump tubing with fresh tubing. So we're going to pause the run, switch out the tubing. Fortunately, the plasma doesn't go out. It's one of those robust plasmas that you can introduce a little bit of air and it won't make it upset. But then we resume the run and let the rinses continue. So the next graph, we're going to zoom in. This is what's going on when you zoom in. So we've cut out, the high level. We're only at 20,000 counts now, which is pretty low. But you see with our initial rinses, our detection limit calculations are based on these numbers. So everything's below 2,000 counts. Now with our first rinse after our high level samples, we get 18,000 counts, and then we go down a little bit. But then, it's slowly going down. So there's a slope the whole time. Even with 12 rinses, it seems like it's still a little bit less each time. So the washout's pretty bad. However, when we do it again, and we've got a spot here, we've got a spot here, this is where we do our second rinse, and we change out the tubing. So now the first half of the tubing that's before the peristaltic pump tubing has really had 2 chances to rinse out mercury and all the other elements. Then we swap out the tubing, and everything from the tubing forth is going to get cleaner. And as you can see, way better counts on this. It's almost as good as our initial rinses. So what happened here? I don't know how many of you actually use ion chromatography. That's actually one of the things I've been working on lately, getting a new system for a different product line. But, those have columns in them. And so you're doing a separation by, separating your analytes through an eluent. That's kind of how the PVC tubing is acting on an ICP. Your mercury starts getting stuck to that PVC tubing, and it's not all rinsing out. So if you completely remove that column and swap it with a new one, all of a sudden your system's clean, because what was happening, it was slowly rinsing out of the PVC tubing and making it to your plasma, even though you haven't run mercury for several samples. So that's probably the biggest cause for washout issues on any ICP. So moving on, for those of you who are using switching valves or syringe drive systems, one of the things you need to keep in mind is sample loops do inevitably become dirty. When they're not in use, you need to make sure carrier solution flows through the sample loops to continuously clean it. So your valve can switch between usually two different positions, where it's inject mode or rinse mode. You want to make sure it's in inject mode, where your carrier solution pumps through the sample tubing when you're not using the instrument. That makes it so the solution in the sample loop isn't stagnant for any long period of time. The more solution you flow through it, the cleaner you're going to get that tubing. I know it's a Teflon tubing. It should be resistant to a lot of elements. The HF elements still stick to it over time. And if you let it sit there, it's only going to make problems worse. The other thing to consider for switching valve systems is the valve sleeve. So that's this piece here or this piece here, depending on the type of valve you have. When routine cleaning doesn't work, you can pop these out and soak them in rinse solutions and clean them with water. If that no longer works, consider replacing those. Those are a consumable item. Depends on how often you use your system. Maybe you should do that monthly or even less frequently, but they get dirty too, and that's something you might forget about. More about switching valve systems. If you're using a sample loop and you're trying to, run something high and you need to rinse it out quickly before you run some other, detection limit sensitive run, believe it or not, you can shake the sample loop while it's rinsing, and you can help clear out any elements that seem to be stuck and left behind. This phenomenon can be observed using the real-time display. So I actually have a video of this. This is from our mass spec with the syringe drive system, but there's some peaks here. I'm going to pan over to show you that I'm literally going to shake the sample loop and see what happens on the real-time display. I actually got some extra signal, so I don't know which element this is. It looks like it might be arsenic or cerium, but when you look at, I shook it twice. You just saw me shake it the second time. The first time I shook it, there was some high signal here. showing that something was left behind and I shook something loose. Second time, it wasn't as severe. So there's less contaminant left behind. And we think that actually gets stuck in the connector that goes to the valve system. So your sample loop has connections on it, might have a little bit of dead space. Elements can get stuck behind there as well. So you got to make sure they're tight, but there might be slight corners that they go through and they might collect over time. So shaking it might help you, get a cleaner system faster. Next is some basic maintenance that everyone should be doing. But I mean, one of the things that we want to point out is that you can soak your spray chambers, nebulizers, valve sleeves in a 25% solution of RBS 25. So that's that detergent solution I've got centered in this slide. 2.5% you can actually run through the system, but when you're doing when you break everything down, 25% seems to be the right amount to recondition your glassware. That's your torch. We've got a torch in here, a spray chamber, and valve sleeves right there, valve parts. All that can be soaked. And then on the left side, we've got an example of the inside of HF resistant spray chamber. That's the coating. On the right side, that's new coating from a spray chamber we got resurfaced. As it ages and we run a lot of HF through it, and actually high acids can do it too, it wears it down and gets less brown. And that can actually turn white. I've run silicon before at 10% HF. It'll turn that white pretty quickly. But if I run stuff undiluted with high HF, I'll get better detection limits if I'm looking for contamination. So some other tips and tricks for washout: keep up with your routine maintenance to prevent your other washout issues. So your torch parts, your cones and your interface, tubing, auto sampler probe, and even your rinse station reservoirs. One thing I like to do before I run trace metals on our OES is actually spray 10% nitric into the rinse station to release any contaminants that might be just coming from the open air, or maybe from the tubing that feeds our daily water cubetainer. I mean, it gets dirty over time and things do leach out of those containers, but pre-rinsing it with a spritz of acid really does actually help get you good detection limits for the beginning of your run. And finally, you should keep a detailed log of your maintenance steps and record performance data. You won't really know how good your instrument's performing unless you log it. So I've got an example of what we use on one of our OESs. So this is a log that we do every morning, since we use this instrument daily. But we've got daily tasks here. So we inspect the torch, we inspect the interface, pump tubing, spray chamber, nebulizer, and we make sure that we have enough rinse in our solution in our rinse station reservoirs, and make sure that our waste isn't going to overflow. Nobody likes a flood in the morning when you get to work, like, oh, we got to clean this up before we can actually run our instrument. But over here, we log the spray chamber that we used, the nebulizer used. These kind of dictate the kind of counts that you expect to see, but also could be the source of washout issues. If you had a bad RSD day, you suspect washout. Oh, it's because I'm using the older Teflon spray chamber. You might be able to trace those kinds of issues. And also what kind of torch you use. Most of them are fixed glass, but they've come out with fully demountable torches, or D torches, where you can change the outer tube and even the injectors. So those have different implications for washout as well. This one has a wave cal. So as you can see, we seem to be doing this weekly. But every day we do take performance data. So we're looking at arsenic, manganese, and lead every day to see, do we get an anomaly? Is something wrong? Sometimes we'll get like 0 counts, even though everything looks good. We discovered there was actually an issue with the nebulizer gas. The actual connection was getting loose and wasn't really actually spraying argon into the spray chamber. We're like, that was pretty hard to troubleshoot, but the fact that we did a daily maintenance run, we kind of were able to troubleshoot that before we had a bunch of runs that went bad. But over here, we've actually got tasks that need to be done as needed. So these are like weekly tasks where we clean the torch. And in this case, I noticed that, we clean the interface a little more frequently. So that's more frequently than once a week. but changing the tubing, spray chamber, nebulizer, and refilling the rinse stations. So one thing to note about the pump tubing, this is one of the systems that actually has a sample loop. It doesn't have a syringe drive, but it does have a sample loop, so it's got a switching valve. So sample doesn't touch the peristaltic pump tubing, only carrier solution, and that's why we're not doing this daily. We're only doing that once a week because the only thing we have to contend with is whether or not the pump tubing gets flat spots. And then, of course, don't forget about other things on your ICP maintenance, such as changing filters. Maybe you have to change the oil on your mass spec vacuum pump. Those are things that you don't want to forget about. So it's wise to keep it on your maintenance log so that you still think about it. And then if you do something weird like a preventive maintenance or you swap out something that you don't normally mess with, a notes section is very helpful. Lastly, some other tips and tricks for washout. Keep several different rinse solutions on hand so that you can handle your high TDS samples more effectively. By doing this, you're going to keep your lab running smoothly to get more done. So this is a picture of a custom rack I kind of made using. I basically used one of CTAC's racks and cut it out with a Dremel tool. You can fit 8 125 ml bottles, and I've got nitric, HCl, RBS, water, and ammonium hydroxide all ready to go. So if I need my method to use one of these other rinses, I can quickly just open it, open the bottle, and use it immediately. So that's very helpful to have, and then you can swap out some of those specialty rinse solutions as well. So some final thoughts. Make sure you identify the elements that give you trouble. We provided a really good periodic table in this presentation. You'll get PowerPoint copies of this. If you're using some of those, identify the problem and then experiment with different rinse solutions. Keep up with routine maintenance. Make sure some of the issues that you're experiencing are not because of something you're neglecting with your ICP. And then identify the specific causes for your washout, whether it be the pump tubing, your spray chamber design, or something else. And finally, develop methods that include effective rinse strategies and include only the elements you require. Changing the order of your rinse solutions, making sure you have enough time. These are all method development activities that are very important if you want to utilize your ICP to its fullest potential. So that's how I'll conclude this webinar today. Want to remind you that we do offer free technical support whether you're a customer or not. So check us out online at inorganicventures.com. We've got an interactive periodic table, sample prep guide, trace analysis guide, an ICP operations guide, and even a forum for you to ask questions. We're here to help you to make sure that you can get your job done as well. Thank you for your time.
Great. Thank you, Thomas, and thank you, James, for the wonderful presentation. We've had a number of great questions come in, and we'll start on those in just a second. Before that, I would like to remind everybody that we will post a recording of this presentation to our website so you can review it in the future. We'll also send a link to every registrant that will give you access to a slide deck of all the slides that were presented here today. And if you have any questions at some point in the future, please feel free to reach out to us and we'll be happy to work with those questions. We've learned a great deal over the years from our customers and the people that we've partnered with. So we really, really do enjoy the Q&A part of this. So we'll go ahead and jump right into the questions. I'm not going to use names and we'll just kind of go through these as they came in. The first one is, what about the stability of lead in the presence of HCl? So Thomas or James, what do you guys think about that?
Yeah, James forgot to mention lead. I noticed that when he was I saw that question come in. Lead seems to be solubility based, so we don't have the specific data for that, but we know that the concentration of lead versus the concentration of HCl seems to matter. What you get is a precipitate. So sometimes you can increase the HCl content or lower it, and vice versa with the concentration of lead to get a solution that'll be stable.
Yeah, I think we've generally seen that lead is a little more forgiving than silver.
It is.
silver, you put 10 ppm and 5% and you may have issues, but with lead, I think it was some of the data we have up to 50 or maybe even 100 ppm in 10%, you might be okay. But when you start getting up to higher levels for like stock solutions or something, you may have issues. But yeah, you can have lead issues, but it's generally a little more forgiving than silver.
Great, thanks guys. Another question regarding mercury. If mercury can become sticky in the presence of nitric in the nebulizer, is this element, can it stick like other elements like calcium, silicon, or perhaps iron? And I think the question really is that are there other elements that can stick in the nebulizer as mercury? And if for any reason I'm not quite addressing the question as I read it, I would ask the participants to please just let me know. Thank you.
Yeah, mercury, it's getting sticky because of the element itself. We have not noticed that calcium, silicon, or iron are specifically sticky elements. Generally, with nitric or HCl, your iron or calcium should wash out pretty well. Silicon's a little trickier. That one depends on your spray chamber. So if you're using silicon, chances are you're using HF, because that's really the only way to get it soluble beyond 10 ppm. If that's the case, if you're using an HF resistance system and you run very high silicon, it'll stick around. It's sticking to that coating, I think, on the spray chamber, not necessarily the nebulizer. But when you're using the glass system, you might not be seeing washout. You might actually be seeing leaching from the material of the nebulizer or spray chamber, and actually even the torch. We recently switched out our D-torch to get it repaired with a glass torch, and we were seeing silicon go all over the place. So it's not just a nebulizer or spray chamber. The torch plays into it as well. And we suspect it's the injector of the torch, not necessarily the outer tube.
Great, thanks. This is a general question regarding lithium. Is lithium a problem? Do we have washout problems for that element?
I think yes, depending on the instrument you're using. So on an OES, I would say no. It isn't specifically sticky. But if you're using mass spec, I've seen lithium gets left behind, and I think it's in the lenses of your ICP, but not your intro system. So when we run trace metals on our mass spec, we usually run 100 ppm, which is pretty high, but we want to see the detection limits get really low for those other elements. And if we run lithium at 100 ppm, we will see it stick around for a month, but it's not actually in the spray chamber. It's not in the nebulizer or the tubing. It's in the lenses, and that takes a long time for it to kind of work itself out. Or if you have the ability to clean your lenses, that's something you might want to consider. If not, you might need to bring in the technician to have him look at that. Because it's so light, it's able to get stuck farther in the system than other elements.
Great. If you are using a basic solution to rinse out elements like boron, how does that affect your run? Generally, most people try to matrix match samples and standards. And with the final sample solution being nitric, do you see any issues with a rinse being basic after running samples that are acidic?
Not specifically. It depends on how much time you use to stabilize your spray chamber. So if you're running that basic solution in between samples, you want to make sure your stabilization time for your samples is maybe a little bit longer, to make sure that the acid has reabsorbed onto your spray chamber. But if you're just doing it at the end of the run, just finish out your runs with water rinses, and that should usually take care of any kind of problems you might see.
Okay, great. So this is it's one part question and one part, I think, great user experience. And this is if you have a double pass PFA spray chamber and you are using a sapphire injector and a ceramic torch, and you can wash away apparently very high concentrations of boron using a citric acid ammonium hydroxide rinse. So this is a suggestion from one of our attendees, and it appears to work very, very effectively. So we want to thank you for the suggestion. Again, I'll just repeat, it looks like citric acid and ammonium hydroxide is a very effective rinse mixture if you want to get rid of a boron memory effect. The question is searching for stability on aluminum. Do you have any suggestions for aluminum washout using this particular configuration? So we're going to go back to Teflon spray chamber, ceramic torch, sapphire injector, and you have this citric acid ammonium hydroxide rinse. And it doesn't seem to be quite as effective for aluminum as it does for boron. So any thoughts, guys?
Well, I've got some thoughts. So obviously the sapphire injector is made of alumina of some kind, right? I mean, that's one of the things that could technically leach off of the injector. So if you're running something caustic, I would imagine that you would be seeing that come out of the injector itself. Um, in that case, it might be wise to switch to maybe something that's platinum tipped. That might help. I know, or maybe switch the injector back to quartz and see what it does. If your aluminum problems go away, you'll know that it's the injector. But I haven't specifically seen aluminum be a washout problem. However, I have seen it leach out of plastics. So one of the things you might also want to look at is make sure you're leaching your sample tubes and any bottles you're using for sample prep, leach them and rinse them with clean DI water to make sure the aluminum you're seeing might not actually be from your sample containers. So there's multiple places that could be coming from.
Great, thank you. A little bit of troubleshooting for that one, it seems. So the next question, we see high signals for tin in background blanks at the start of a run, and then the signals go down during the run. What can we do about this? And this kind of came about during your discussion of using a mixed acid rinse, 2% nitric and 1% HCl. So again, high tin background at the beginning of the run decreases throughout the run.
James, do you have any thoughts on that?
And I'm assuming this is clean system, or are we talking post maintenance, or is it maybe from the day before? But I mean, it makes sense. If you're doing a run, you're probably going to run across a number of different acids that are going to help wash it out eventually. But as far as why it's there in the first place, that may point to a maintenance issue. I can think off the top of my head.
There's another thing I'm thinking of. Tin is in the back of my head. We pick on tin a lot because it's one of the easier HF elements to destabilize. It'll hydrolyze out if it doesn't have enough HF. Try rinsing with a little HF if you're allowed to use HF. If not, increase the HCl. But if you see higher tin when you increase your HCl, suspect your HCl. I've done a lot of trace metals on acids and bases over the years, and I have noticed that tin is a common contaminant in HCl. So you might want to get a sample of some of that C star acid or Optima grade acid, whatever they call it, that's been doubly distilled, and see if your tin goes down or your tin problems go away. I'm also suspicious it's actually in the lenses of the mass spec or the quadrupole. I've seen it more on mass spec than OES, but you might be able to blame the acid as well.
Okay, great, thank you. A couple of questions now about tubing. So this one is regarding ismaprene tubing, or ismaprene, maybe the correct pronunciation, I'm not really sure. So this is essentially a pharmaceutical medical grade tubing. It's, my experience is it's the brown, opaque peristaltic pump tubing, and it's a polypropylene based elastomer. So I know that we have not really used that much here in the lab, guys, but do you have any ideas about using pump tubing that is not your typical clear plastic, or might be used in more of a pharmaceutical or food grade application?
The first thing I can think of is you may want to kind of allude to what Thomas was talking about earlier with the live time. If you're using some tubing that you're not familiar with or is new, you may want to do a little playing around on your system where you do some of that live monitoring of some analytes as you run maybe a few different matrices through it to see how it's going to react. And because that's the first place I'd go anyway, thinking about something like that, so you can rule some of that stuff out before you start doing analyses. Thomas, you have any?
Yeah, I think the real-time display is going to be your friend in this case. When you can, if you're able to swap out the tubing while the instrument's running, see what new tubing looks like versus tubing that's maybe been used for a week and been rinsing with your rinse solution or carrier solution, and see if there's a major difference with certain elements. That'll take a lot of work though, because there's only so many elements you can look at on the real-time display. But you might be able to set up some kind of run that monitors the elements that you care about, and just have it sample at certain points.
Okay, great. So continuing the tubing discussion, do you switch out just the pump tubing or all of the tubing, including the sample probe tubing, tubing going to the nebulizer, et cetera, when you're really trying to deal with washout considerations? Is it necessary to do that?
Generally, it's the peristaltic pump tubing that's the major offender. But as I mentioned before with the sample loops, all that other tubing is the same kind of tubing. It will get dirty over time, but it is much more resistant than the pump tubing. It's just because of the material itself. The PVC is, I don't know, it's a softer plastic. It must, because it gets rotational wear and tear from the peristaltic pump itself. It's going to get cracks in it. It's going to hold stuff. Whereas that other tubing that goes to the nebulizer or goes to the auto sampler is much hardier, and not much sticks to it. Things do stick, but you should be able to wash that out with a couple rinses.
Okay, great. Moving on to RBS 25, have you heard of any issues using RBS 25 with Miramist nebulizers or a nebulizer specific issue with RBS 25?
Not. I have not heard of any issues. I know that's the recommendation Glass Expansion has for most of their nebulizers. I'm not sure which one the Miramist is. I think that might be the smaller one. Um, Generally, when you've run the RBS 25, I'll just say you're supposed to run a lot of water, and not a nitric rinse or an HCl rinse. The water is more helpful for doing a final conditioning of your spray chamber and tubing and whatnot. So, if you're having any issues using the RBS on that nebulizer, maybe cut down the concentration or run water for an extra amount of time than what you were doing before.
Okay, great. What do you recommend using for calibration standards and washout when analyzing for elements that are stable in nitric and those that are stable in basic solutions, such as boron?
Okay, so boron we said is one of those basic elements. It's fine in nitric and HF and HCl depending on how high the concentration is. So the only time I know of that it doesn't really work in the nitric is if it's a below if I think it's 5,000 ppm. I know standards above 10,000 ppm or they just don't work unless you're in a basic media. Um, so I would say, with washout, just switch to the basic solution. But when you're running the samples, acid should be fine. Um, Even low levels, I haven't had issues on the mass spec with boron. Um,
Okay, great. Thank you. Next, bismuth. I have problems with bismuth because I use it as an internal standard and problems with mercury. I'm going to start using gold. What do you recommend for bismuth?
Increase the HCl some, unless you're looking at arsenic. um, Maybe get in touch with us about what you might be able to do. But the gold, even gold in nitric has chloride in it. So be mindful of that. There's no gold out in this world that doesn't have chloride attached to it. It's one of those precious metals that just doesn't behave without it. Um, with the bismuth, just increase the HCl and see if that helps. I know when we're doing very low level bismuth, like 1 to 10 ppb, that level will actually stick to the tubing, and that's even with the syringe drive system that doesn't use PVC. But when you use HCl, it seems to help it. So increasing the HCl, I think, will be your best bet, and that'll help with your mercury automatically.
Excellent. And this is similar to, I think, an earlier question, which is just basically, is it ever acceptable to use a basic solution rinse after analyzing acidic samples? And Thomas, I believe the comment is just make sure your timings are set appropriately. You have a long enough time to stabilize the solution and copious amounts of water.
And use both.
Okay.
Just alternate between the two and see how it behaves, and you'll see which elements are happy with one versus the other, and a combination of both is going to get you through.
Great, thank you. So those appear to be all the questions. If there are any others that we've missed, you have an opportunity to submit those still in the Q&A feature. There are a couple of comments. I do want to mention these as well. The first one is regarding thorium stability, and this is from Steve Pavis. For those of you who maybe aren't familiar with Steve, and I'm going to call you out, Steve, he is an expert's expert. He is a regular contributor to the Plasma Chem list server, has a great deal of experience with ICP analyses, and I can say that I learned a lot from him many, many years ago when I was alone in a lab with an ICP and didn't know what I was doing. So thank you for being here today, Steve. His first comment regarding thorium was that in the absence of HF, it's going to be present as a poorly soluble oxide. And if you add a little bit more HF, you end up with a poorly soluble thorium fluoride. And then Steve published a paper which details adding even more HF to get to a soluble thorium fluoride compound. So this is really interesting, Steve, because one of the things is that, you know, there's a titration for fluoride using thorium in water samples, which is very, very old. And it appears that your comment is that if you're having issues with thorium stability in the presence of HF, you can just keep adding HF and you'll drive the thorium back into solution. So if you have an opportunity to maybe jump in and confirm that, that would be great. Another comment from Steve is just regarding switching valves and rotors on some of these sample introduction systems, and that they can accumulate small quantities of insoluble silica from plant or geological samples that can also grab some metals. So it looks like he has some experience with these switching valve systems, and that you need to be careful about kind of what would appear to be long-term memory issues, and particularly related to insoluble silica. So that's super fantastic, Steve. Thank you for that. A couple more questions have popped up, so we'll start on those. If my highest concentration in a multi-element standard is 1 ppm for optical emission, and we're not using mercury, bismuth, you're using internal standards, scandium and gallium, are there any washout concerns for elements at that level? And I'll repeat this for the panelists. Highest concentrations in an OES multi-element standard are 1 ppm. Internal standards are scandium and gallium. Are there any washout concerns at that 1 ppm level?
No, I would say we routinely do such a strategy for trace metals. We have a standard that's at 100 ppb and 1 ppm for a calibration curve. I've never seen washout problems with that method, and that's using glass or HF resistant system, glass or detorch with ceramic. It all 1 ppm or lower is going to be okay on the OES, I think.
Yeah, I agree.
Great, thank you. So the next one, tellurium. Does tellurium form a stable chlorocomplex if the chloride concentration, the HCl concentration is high enough? And the example is, let's say 30%. And I think we know the answer to that one.
Yeah, we actually have a stock product for tellurium. I believe it's a 10,000 ppm, and it does come at 30% HCl. We have, I think, if I'm not mistaken, we have 3 different flavors of tellurium. One of them is in hydrochloric acid, with the other being in straight nitric, and one in nitric and in hydrofluoric acid. So
yeah, if you want high tellurium, HCl or nitric HF is the way to go. And if you don't want to use either of those, you're limited to 1,000 ppm, and you can do tellurium in only nitric, but it will likely be stickier. Tellurium is one of the ones I've identified as a sticky element. So in order to wash it out, you're going to need to increase the HCl or increase the HF, do something else to try to get rid of it. Probably the PVC tubing.
Great, thank you. Is it acceptable to have a rinse solution that contains 1% nitric and 0.5% HCl, or is it best to aspirate these rinse solutions separately?
No, a combination of both is perfectly appropriate. It depends on what you're doing for interferences. Like I said, HCl is avoided on the mass spec for specific reasons. The arsenic and selenium come to mind, but if you're not checking for arsenic and selenium, you're not going to care. But the mixture is going to help because there are a lot of things that are okay with nitric, and there are some things that need the HCl. So mixing them together is just going to make things easier for you.
Great, thanks guys. I think this might getting down to the end here. I'm considering using peroxide for sample preparation for a low-level silicon analysis by mass spec. Is there an appropriate range to keep that peroxide concentration at or below for mass spec work?
I am not sure about an appropriate range. I have run it before without any issues. One thing I will say, there is a paper, a white paper by Agilent out there somewhere. It's very hard to find, and it took me a long time to re-find it to do a rinse solution. They actually have a rinse solution they proposed for mercury, and it's just dubbed as Agilent cleaning solution. It has nitric, it has HCl, it has EDTA, it has peroxide, it has ammonium hydroxide. It's basically got the kitchen sink in it. But like I said, it does have peroxide, and that solution works pretty well. I think it also has Triton X100, so that adds the detergent capabilities that RBS has, but without all the sodium. So you might want to try to look for that white paper. And if you have difficulty, just reach out to us and we'll try to help you out with that.
Right.
A lot of
And
components.
one,
Basically holy water.
what was that, James?
I was saying it's basically holy water. That's a lot of it's a lot of cleaning power.
Not much water.
Yeah.
So I will just follow up with that. Have we ever noticed any type of contamination issues with using peroxide? And would that be a concern if it's part of your sample prep?
Absolutely. So one of the things we've learned over time, we made this discovery a long time ago. You can get two different kinds of peroxide. There's something they call stabilized, and there's one that's unstabilized. You need to purchase unstabilized. The only thing you have to worry about is keeping it cold to make it preserve longer. The stabilized, they put a lot of sulfur components and a bunch of other junk that makes it really hard for you to do trace analysis or provide clean standards. So if you go with unstabilized, it's usually just water and peroxide.
Great.
No additives.
Well, I believe that was the last question. We do have Thomas, I think this is in relation to your comment. Optimizing sample throughput in ICP-MS by Wilbur, Agilent Technologies. This is an Agilent ICP-MS journal, May 2006, issue 27. So I'll just repeat that for the attendees. This white paper is from the Agilent ICP-MS journal, May 2006, issue 27. The title, Optimizing Sample Throughput in ICP-MS by Steve Wilbur. If you have any questions about that or weren't able to capture that, please let us know, and we'll be able to provide that information. And thank you so much for the attendee who sent that in. That is super helpful. It's why these events can be so remarkable in helping us all learn. It's a community out there, and the more we share information, the better off we'll all be. So thank you very much for that. If there are no other questions, and I think that kind of captures everything that has been presented, I want to thank the presenters once again, Thomas and James. You did a great job. For all the attendees, thank you so much for joining us. We will have more webinars throughout the year and hope that you'll be able to join us then. And please, if there are any questions that we were not able to answer or that might come to your mind a little bit later, please reach out to us and we'll be happy to work with you and see if we can help. So thank you for your time and attention, and we look forward to seeing you again at our next webinar. Thanks.
Thank you all.
Thank you, everybody.